Okay, welcome to the Tutte Colloquia. Today we're very happy to have Alexey Pokrovskiy, who joins us from the mathematics department at University College London, where he recently moved. Alexey's research interests span a wide range of discrete math and combinatorics. And today he'll tell us about Rota's basis conjecture and how it holds asymptotically. Alexey.
Thank you, David, and thank you very much for the invitation, all of you, for coming here. I'm going to tell you about a problem from matroid theory called Rota's basis conjecture. And I'll start with giving some special cases of this conjecture, which are appealing. So one very easy special case is about simplices in real vector space. So say you have a collection of simplices in R2, so a collection of triangles in R2. We think of each of the triangles as having a color, and we really care about the corners of the triangles. How many rainbow simplices can you find here which are disjoint? So rainbow simplex, always a rainbow object for today, will be one where each of its corners have different colors. So in this case, you can find 3 disjoint rainbow simplices, so you can decompose all your points into rainbow simplices. This is a conjecture that you can do in general. A second problem is very close related. If you have bases in a real vector space, so say R3, you have 3 bases, how many disjoint rainbow bases can you find? In this case, a rainbow basis is one which has 1 vector from each of the original ones. And again, the conjecture is n, and this is actually what Rota initially conjectured. This is why it's called Rota's basis conjecture. Later, he made a generalization to matroids. In this case, you can see 3 rainbow bases where the rows of what I've drawn. There are 3 bases. A third example about graphs, and this example will be important for this talk because when I talk about the proof later on, I'll give you some examples, and I'll always use this as the example. So say you have spanning trees in a graph. So say you have 5 vertices here and 4 spanning trees. And again, you think of the original object, these spanning trees, as each having a color. So say here you have a red spanning tree. How many disjoint rainbow spanning trees can you find? And again, the conjecture is you can get n of them. So here are 4 disjoint rainbow spanning trees. All of their edges have different colors. So these are 3 examples of what Rota's basis conjecture implies. I wasn't sure whether to define matroids in this seminar, but I think I'll briefly give it to you in case someone doesn't know it. For people who do know matroids, think of this slide as a summary of everything about matroids that I will use in the proof later on. So what a matroid is, it generalizes the 3 settings in the previous slide. It's always defined on a ground set, and it's a subset of subsets of the ground set. So you can think of it as like a hypergraph, but instead of hyperedges, we call the members of the matroid as independent sets. And there's 2 properties. One is that you're downwards closed, so a subset of an independent set is still independent. And the most important property is the augmentation property, which is that if you have 2 independent sets of different sizes, you can move an element from the bigger set to the smaller set. This is, for example, a property which independent sets in a vector space have. Let's just think about the graph example from the previous slide. The way the matroid works there is you have a graph, and the matroid is a set of all forests on the edges of the graph. So the ground set of the matroid is the edge set of the graph. So here are all the forests you can put on this graph. And the 2 properties are a subset of a forest is also a forest. And if you have 2 forests of different sizes, you can move an edge from the bigger one to the smaller one to get another forest. And to state Rota's basic conjecture, you need to know what a basis of a matroid is, and that's a maximal independent set. And like a first exercise in matroid theory is that all bases have the same size, which is called the rank of a matroid. This comes from the augmentation property. If you have 2 independent sets, you could always move something from the bigger one to the smaller one. And because of this, all maximal independent sets have to have the same size. And now we can state Rota's basis conjecture, the general form, which is if you have n bases in a rank n matroid, you can find n disjoint rainbow bases. This generalizes the three examples from the first three slides. So I'll briefly survey what's known about this problem. And please, if I skip some results here, inform me either in the chat or by email, because there's a lot of literature in the conjecture, and I'm not the biggest expert on everything that's been done. So I would be very interested to hear of any results which I'm not mentioning here. So first, one approach towards the conjecture is to prove it for some special natural classes of nitroids, and there's been work here. There's one result which I'll highlight, which is that we know it for representable nitroids whose rank, so this number n, is a prime number plus or minus 1. This is done in a combination of works. First, a representable nitroid is this vector space example, which is the second example I gave you. So there's two works which combine to give you this, one by Huang and Rota, where they reduced the conjecture for these representable nitroids to something called the Alantarsi Conjecture, which is a separate problem. And what Driscoll and Glynn did is they proved the Alantarsi Conjecture with these numbers, which are prime plus or minus 1, which together this gives us this result about Rota's basic conjecture, which in my opinion is very strong evidence towards this conjecture being true. So this is what's known for special classes of matroids. Another approach to the problem is to look at general matroids and try and prove partial results, but which hold for all matroids. And there's lots of different approaches you could take here. So one is you can think of the conjecture as like a packing problem. You're trying to like pack disjoint rainbow bases. And you could ask how many can you actually prove that you can pack like this. So Gielen and Webb showed that you can get root n disjoint rainbow bases. Dong and Gielen improved this to n over log n using a probabilistic argument. And a couple of years ago with Bucic, Kwan, and Sudakov, we improved it to about n over 2. So roughly half of what Rota asks for. So this is one approach. Another approach taken by Aharoni and Berger was to think of the conjecture as a covering problem, where you want to cover the whole matroid. So the matroid has n squared elements in total. You want to cover them all using n bases. And you can ask, what if I'm allowed to use more than n independent sets? Can I cover all the elements then? So Aharoni and Berger showed that if you have twice as many independent sets as you want, then you can do it provably. And a couple of years ago, there was a polymath project, Polymath 12, which looked at this Rota basis conjecture. And one of the results that came out of that was an improvement to the Aharoni-Berger bound to 2n minus 2. Okay, so we'll today be looking at something that's a little bit weaker than all of this, but also a very natural question. And the question is the following. So you have n squared elements in the matroid in total. When is the graph case of the conjecture known? So this is a question by Karen Yates in the chat. Off the top of my head, I think it's known basically when the graph matroids are they a special case of representable matroids. So this would be the best result, if I'm not mistaken. Or if not, maybe somebody can in the chat write what is the best thing that's known about the graph matroids. But good question. So, right, so today we'll be looking at the following question. So you have n squared elements in the matroid, and you want n independent sets which cover all of them. And the question is, how many elements can we prove that you can cover with n independent sets? And all of these previous results here say something about that. So for example, this last result about packing bases, well, these n over 2 bases will, of course, cover n squared over 2 elements. So at least naively, that's the bound that you get from here. So you can cover n squared over 2 elements using this result. You get something similar using these covering results as well, because if you have 2n independent sets which cover everything, then by the pigeonhole principle, the n biggest ones of them will cover also n squared over 2 elements. So from these previous results, you can cover about half of the matroids using n independent sets. And what I'll be talking about today is the following theorem, which shows that you can cover almost the whole matroid using n independent sets. So you can cover 1 minus epsilon times n squared. So this gives an asymptotic version of the conjecture. It shows that something very close to the conjecture is true. And going forward, there'll be a lot of interesting results, I think, in particular to prove stronger asymptotic versions along the lines of these previous lines of research, which would be stronger than this. So if you could find 1 minus epsilon times n disjoint rainbow basis, that would be better. And if you could cover the whole matrix by 1 plus epsilon n independent sets. Are the n bases in the conjecture pairwise disjoint? So yes, sort of. So this should give an answer to this problem. So here you have 4 spanning trees, and they're not disjoint in some sense in that you have some edges which are present in 2 different trees, but when you have 2 edges in 2 different colors, we think of them as being different matroid elements. So they are pairwise disjoint in that sense. Okay. So for the rest of the talk, I'll talk about the proof of this. So let me mention that previously we only knew asymptotic versions of the conjecture for some special classes of matroids. So for example, for representable matroids, we knew that it's held asymptotically as a consequence of the conjecture being known for prime values. Basically, because if you have a vector space, you can always embed it into a vector space of prime rank, where the rank will only be a little bit higher than the original rank. This is a consequence of the prime number theorem. And because you know the conjecture for prime rank vector spaces, you get an asymptotic version like this one for all ranks. Okay, so for the rest of the talk, I'll talk about the proof of this theorem. Hold on. And my goal will be to, so I won't have time to show you the whole proof, but my goal will be to show you where all the matroid theory will be used. And the bits I won't show you will essentially be a calculation, which you need to add to that. So just to summarize the setting for everything I write will be the following. You have a colored matroid, you have n colors, they're independent sets of size n, and you want to find n rainbow independent sets which cover a lot. So just to give you a picture, to remind you how it looks, here's a colored matroid, so just have this as a picture of a colored matroid, spanning trees in a graph. For Rota's conjecture, you want to find n independent sets which cover everything. For us, we'll be happy with covering almost everything, so you can skip a few edges. Okay. So this is the setting. I'll talk a bit about the structure of the proof. So unfortunately, it's a proof by contradiction, so it's a little bit indirect. So I'll first say kind of what we're actually trying to prove and why it gives a proof. So the objects which we'll be working with are what I'll call a maximum family. And this is a family of n disjoint rainbow independent sets. So for the proof, we want a family like this, which has size 1 minus epsilon n squared in total. What we'll be looking at are families which are just as big as possible. So with as many total elements as possible. So we'll be studying maximal families because what we want to prove is that maximum families have 1 minus epsilon times n squared elements. So that's what we're trying to prove. And the way the proof works is it'll be a proof by contradiction. So we'll suppose that maximum families have less than 1 minus epsilon n squared elements, and then we'll prove different properties of maximum families, which eventually will lead to a contradiction. What kind of properties of maximum families will we prove? We'll prove that you can move elements within a maximum family to get new maximum families. And eventually that will allow us to add elements to maximum family to get a contradiction to this maximality condition. How can you add elements to maximum family? So there's one very, very trivial way to do this, and I will write this here. We'll call this a triviality, which is that, say you have a maximum family. So I'll denote this as I1 up to IN. So these are the independent sets that the rainbow independent sets in the maximum family. Then if this is a maximum family, then certainly something that cannot happen is you cannot have an element from outside of the maximum family. So there is no element from outside of the maximum family, which you can add to one of these independent sets to get something that's rainbow and independent. Just because if you could add an element to one of these independent sets, then you could replace that independent set with it plus this element to get a bigger family of disjoint rainbow independent sets. Just to give you a picture of what this means. So here is a colored matroid. Here is a family of rainbow independent sets. If it doesn't cover everything, there'll be some remainder. So there'll be some elements which are outside of the family. And if you can move something from the remainder to one of the independent sets, then that shows you that it's not a maximum family. Okay. So what can we do with this triviality? One consequence of it is that it shows that if you have a maximum family which doesn't cover too much, then you can move elements around with that maximum family to get other maximum families. So the corollary of this trivial fact is that if you have a maximum family, so which is small, so the total number of elements in the family is less than 1 minus epsilon n squared. So let's suppose for contradiction that maximum families are smaller than this. Then the consequence is that there are at least epsilon squared n squared elements in the family, which you can add to some of these independent sets in the family to get something that's also rainbow and independent. So basically, there's quadratically many elements which you can move around in the family to get other families which have the same size. So why is this true? So it comes out of this fact. So it happens because, so just by averaging, if the maximum family is small, then some set in it will have to miss linearly many elements. So by averaging, some set in the family has to miss epsilon n many colors. But from the augmentation property, so each of these colors, it has n elements, and this independent set has 1 minus epsilon times n elements. So from each of these missing colors, you can move epsilon n elements into this set. So this you get that each such color has epsilon n elements which you can move into the independent set to get a new rainbow independent set. Okay, so this is a very simple fact which just tells you that you can move some elements around in maximum families. And these two triviality and corollary, it'll be important because the more advanced proof I'll show you later will have a similar structure to what we just did here. Okay, so now the next bit which I'll show you will be a definition, and this definition is very important. It's the definition around which the whole proof rests. So I'll first give you a definition, then I'll give you an example of, like in an actual map, right, of how the definition looks like. The definition is, you have a family of disjoint rainbow independent sets. And the definition will be an operation which you perform on this family, which I call K-reduction. So we define a K-reduced family, which I denote as F subscript K primed. So this will be a new family, which you get. And how you get it is you start with the family F, and you delete. So Liana Yepremian asked, why was every color missing epsilon and many? So
I just mean the second one. Why is it that for every such color you have this property that you can?
It comes from so every color has n elements. This independent set misses epsilon n elements because it misses this many colors in its rainbow. So it has size 1 minus epsilon n at most. And then you have a independent set of size n and independent set of size 1 minus epsilon n. And from the bigger one, there's going to be epsilon n many elements which can move into the smaller one. It's kind of from you iterate the augmentation property to get this.
Okay. Mm-hmm. Okay, thank you.
Yeah, great question. Thanks. Okay, so this operation of reduction, it starts with a family and it makes it smaller by deleting elements from it. So you take F and you delete some elements from it. So you minus all elements with a particular property. So the property is that for each of the elements which you delete, you have you can pick some independent sets in the there's a lot of independent sets in the family to which you can move them. So you can pick K sets in the family where you can move this element and still get something that's rainbow and independent. Okay, so this is this operation of reduction. So the picture is you have a family and it becomes smaller. I'll give you an example in a second. And how it becomes smaller is any element which you can move in K different ways, you delete it. And just a bit of notation. I'll use the notation F subscript K with a T in brackets to denote what you get by repeating this operation K times. So you take with a family and you apply this operation to it K times, one after another, or T times. Okay, let's look at an example of this. Here. Okay, so here's a matroid, and here's a family. Let's think about what happens when you reduce this family. Here's a definition of the K reduced family. And we'll just think about the 1 reduced family, so when K is equal to 1. So 1 reduced family, you delete all elements for which there's at least one different independent set to which you can move that element. So you'll end up deleting some elements here, and here the dashed elements are the ones which get deleted. So for example, let's go through them. So this light blue edge here, it can be moved to this independent set, so it gets deleted when you reduce. This dark blue one can be moved here. This light green one can be moved here to get something that's rainbow and independent. This red one can be moved here, and this light green one can be moved here. And for all of the other elements, for example, this light blue one, wherever you move it, you'll either violate the new independent set being rainbow or independent. So when you one reduce this family, all these dashed ones get deleted and you end up with this family. And then you can one reduce the family again, which means you now look at this new family, and anything here that can be moved to get a new rainbow independent set, you delete that. And actually everything here, you can move it somewhere to get a new rainbow independent set. So for example, this green thing can be moved here or here. So everything gets deleted, and the the twofold one reduced family ends up just being a collection of empty graphs like this. So that's how this reduction operation works. You start with a family, and as you iterate this operation, it gets smaller and smaller and smaller. And just let's go back to the start. You could also think about two reducing the family. So there the operation would be, you delete any element for which there's two different places where you can move it. And then you can see this actually won't change the family, because for every, say that for the light blue edge here, you can move it here to get something rainbow and independent, but you can't move it anywhere else because these guys already have a light blue. So this light blue won't get moved in the two reduced family. And so the two reduced family you can check here is just the family itself. So as k gets larger, the rate at which the family gets smaller as you reduce slows down. So that should give you some intuition of how this looks. Okay, back here. Okay, and let me actually go back to this corollary, and let's phrase it in terms of this operation of reduction. I just want to keep this. Let's, let's phrase this corollary in terms of the operation of reduction. So what it said is there's a lot of elements in the family which you can move to some independent set in the family. So you could rephrase it as saying that the number of elements in the one reduced family, so F1 prime, is going to be at least epsilon squared n squared smaller than the original family. So it's at most the number of elements in the original family minus epsilon squared n squared. That's just a rephrasing of this last two sentences of the corollary. Okay, and now I can actually tell you how the whole proof is structured. The goal of the proof is to show that when you apply this reduction operation over and over again, the family gets small very quickly. So basically, you want to show that as you keep reducing, you keep losing epsilon squared n squared edges. That turns out to be enough to prove the theorem. So what we want to prove is that for every epsilon bigger than 0, and for some parameterization between k and t, which won't mean anything yet, but the important thing is that for any fixed values of these three constants for sufficiently large n, the following holds. So if you have a maximum family, which is small, so we're supposing for contradiction you have at most 1 minus epsilon times n squared elements, then whenever you reduce that family, you lose quadratically many elements. So if you look at the t plus first reduction and compare that with the tth reduction of the family, you lose quadratically many elements. Right, so this is what the proof amounts to proving. And if you can show this, then this implies the theorem, because this gives a contradiction when you set t to be equal to 1 over epsilon squared. See, you fix epsilon, you set t to be 1 over epsilon squared, then you just choose k to be large enough, and then you also choose n to be large enough relative to those three. And then if you have a maximum family, which supposing for contradiction has less than this many elements, then this inequality will hold for every value of t in that up to that value. And by putting all these inequalities together, you'll get that the t plus first reduction has a negative number of elements, because these epsilon squared n squared terms will add up. So you'll say that this has to be a negative number of elements, which doesn't make any sense. So that's a contradiction. So that's the structure of the proof. So the proof amounts to studying this reduction operation and showing that it deletes elements quickly enough. Okay, let me see which time we got. We've got loads of time. Okay, so now I'll show you two lemmas which kind of go towards giving us a bound on the number of elements in the reduction. And the lemmas there'll be some parallels between them and between these ones. There'll be in some way strengthenings of these facts. So the first lemma will be a direct strengthening of this trivial fact. So let me write it down. The lemma is that if you have, so for some dependency between k and t, if you have a maximum family, so this will look a lot like this triviality. So again, you have a maximum family, and then we'll get a conclusion which looks a lot like that. So the conclusion we'll get is that there is no element E which is outside of the family, which you can add to an independent set to get something that's rainbow and independent. And this is exactly the same as this. So it said there's no elements from outside the family which you can add to an independent set to get something rainbow and independent. The difference is that, oh, I should hide this. The difference is that here, this independent set to which we were adding was in the family, whereas here, in this lemma which we proved, the independent set is in the reduced family. So in any reduction of the family. So it's in Fk to the t. And this is a stronger statement than this triviality, because right, when you reduce the family, you're deleting elements, right? Remember the example, when you're reducing the family, you're losing elements. So it's a stronger statement to like there'll be more elements which you can add to independent sets in the reduced family to get new rainbow independent sets. So this lemma is strictly better than this trivial fact. Okay, so let's talk about the proof of the lemma. So the proof. I'll show you the proof for t equals to 1. And I'll talk about how it works in general. So t equals 1 means you just do the reduction operation once. So it's just what's written here. So you just reduce it once rather than iterating it. So if you have an independent set in the k reduced family where you just reduce it once, then is going to be naturally contained in some independent set in the actual family, the maximum family which you start with. And so there's like a natural containment between the independent sets in a reduced family and the original family. Okay, so we know that you have an element which when you add it to I, you get something rainbow independent, but J is bigger than I, so we don't know that when you add E to J, you get something that's rainbow independent. But what you can do is you can delete some elements from J to make it rainbow independent. So there exist two elements in the bigger independent set, which you can delete from J, and you can add E to get something that's rainbow and independent. So we're not actually using anything about where J comes from for this. So this holds, you can do this for any rainbow independent set. So if you add E to J, so J was rainbow independent to begin with. So when you add E to J, the color of E might have been used there. So we could just delete the element F1, which share the color with E. And secondly, when you add E to J, it might create a dependency, but you can always delete one element to get rid of that dependency. So you can delete two elements and replace them by E to get a new rainbow independent set. Okay, now we're going to use the definition of K reduced. So we'll use this definition here. And we'll apply this definition to these two elements, F1 and F2, because they lie outside of I. I is in the reduced family, right? I is in the reduced family. F1 and F2 lie outside of that, so we can apply this definition to F1 and F2. What does that give us? It tells us that there's a lot of places where you can move F1 and F2. So there have to be K choices of independent sets to which you can move to get something, F1 and F2 to get new rainbow independent sets. Okay. So let me now draw a picture of how you will now get a contradiction to maximality. So the picture here is you have your element E, and we can move this to J. But in J, we have elements F1 and F2. Which we want to delete from J. But rather than just deleting them to be able to add E, we're going to move them out of J. We move F1 to I1, and we move F2 to I2. Right, and we can do this. So we can do these last two moves from here, and we can move E into this using the previous line. And if you do that, you get a larger family of independent sets, because when you move F1 and F2, you're not changing the size of your family. So it's still going to be a maximum family, but then if you add E into that, you're increasing it by 1. So that gives you a contradiction. So this contradicts maximality.
Actually, why is this second thing true? Can you explain it again?
Which one? This one?
Yeah, why?
So this is coming
the existence of F1, F2.
Oh, sorry, this
you
one.
Can just take away. Yes.
This line? Yeah, so when you imagine adding E to J, so J is a rainbow independent set. So when you add E, there might be at most one element on J which has the same color as E. And we delete that element, and then you can add E. So say F1 shares the same color as E. You add E, delete F1, and now you don't have that. Then you still have a rainbow object now. There could also be one element which is dependent with E, which you can delete that. So that's why those at most two elements which you delete. Okay, so you get a contradiction to maximality. That's the proof for T equals 1. For larger T, it's kind of like an induction. So what happens is, I won't like really say anything, but how it looks is you, rather than just moving these elements here, you're going to also want to delete stuff from these sets. So you find like a G1 here, G2 here, G3 here, G4 here, which you then move to some other set. Let's call them L1, L2, L3, L4. So it kind of, for larger T, just looks like a kind of bigger binary tree, the way you move things. And the place where you use really this definition of reduction is you want to choose K large enough so that you can pick all these independent sets to be different, so that there's no like conflict between where you're moving things. And that's where this bound, exponential bound of K is bigger than 3 to the T comes from, because you want kind of everything here to be different. Okay, so that's how the proof of this lemma works. Okay, now let me show you. So this lemma was like an analog of this triviality. And remember, what we're really aiming for is to try and understand how many elements you have when you reduce the family, and to show that you lose a lot of elements. So the next lemma, it won't imply this very immediately, but it will give us some information about how many elements you have when you do a reduction. And so the lemma is, again, for this dependency between K and T, if you have a maximum family, and you have a color, and you have an independent set, which is part of the T reduction of this family. So you reduce it T times, which misses this color. Then what the lemma tells you is it gives you a relationship between how many elements the color has in the T plus first reduction and the size of this independent set. Right, so it tells you that in the T plus first reduction, the color has less elements than this independent set you had. So the point of this lemma, you shouldn't really like digest exactly how it's related to things, but it gives some kind of relationship between the number of elements you have when you reduce T plus 1 times and the number of elements you have when you reduce T times. So this is not immediately close to what we're going for. We want really just to show that when you reduce T plus 1 times, you lose quadratically many elements. That's what you want to prove. And it's not immediate to get from this to this. So like you'd really want that on the right-hand side here, rather than having the size of this independent set, you'd like something like it, just to have the number of colors here minus maybe in a linear term, something like that. That's not what we prove. Instead, we prove this more complicated thing. And to get from here to here, it's just a kind of a counting problem. So to get to here, we don't use any more matrix theory. So after we prove this lemma, you just need to think about what's the best upper bound you can get for the number of elements in the T plus first reduction relative to the Tth one, if this is what is the best you know about the number of elements every color has. So it's a fair bit of work, and that I'm not going to be able to show you, but I'll show you the proof of this lemma. So the proof of the lemma is a lot like the proof of the corollary we saw earlier. And I'll only show you this lemma, which you prove it when this number K is equal to 1, so the 1 reduced family. So how does it go? Okay, so this independent set has size I, so there has to be n minus the size of I elements, which you can add to this independent set to get something that's rainbow and independent. So this just comes from the augmentation property. So if you have an independent set of this size, remember the missing color, in the missing color you have n elements. So the difference of that is the number of elements you can move from the missing color to this independent set. And what the previous lemma tells us is that all of these elements have to actually occur on the maximum family. Right, so if you go back to the previous lemma, it tells you that if you can move something onto an element in the reduced family, then this element it couldn't come from outside of the family because you have this maximality condition. So it tells you that any element from a missing color you can move to this independent set, it had to be in the original maximum family. And then from the definition of the T plus first reduction, you get that all these elements have to be absent from the T plus first reduction. So from this definition. Because you can move all of them onto this independent set I, which is in the T reduction. So then you just count how many, what that tells you about the number of colors or the number of elements that the color C has left. So you get that the number of remaining color C elements is going to be at most the number of elements that the color had at the start minus the number you learned that you're deleting here, which is n minus I, which simplifies to give you this equation that you want. Okay, so that's how much I'll say about the proof. So what I've told you is all the points where the matroid axioms are used in the proof. So the rest of the proof, it's all about looking at this inequality and thinking about what's the best bound I can give on the number of elements in total in the T plus first reduction relative to the T one. The kind of way that does it is, so this lemma, it gave you some choice about this independent set I. So for every color, there'll be some particular independent set which gives you the best possible bound here. And you kind of need to do an optimization problem over all such sets. Okay, so that's what I'll say about the proof. And now I'll just mention some open problems to end with. So the open problems I have on this slide are all about proving better asymptotic versions of the conjecture. So one natural thing is to just improve the bounds. The proof that I have, it gives a bound of n over root log n for the how much you cover, and it would be interesting to improve this. I haven't really tried too hard to improve it, so yeah, I think any kind of improvement would be interesting. Secondly, there are qualitatively better improvements you can also look for. So such as you might want to actually find disjoint rainbow bases rather than rainbow independent sets. This is harder. And another direction is this kind of covering version of the problem where you want to really cover all of the elements in the matroid using just a little bit more than n disjoint independent sets. So all of these are harder than what I've been talking about, but still maybe the arguments would be a good starting point for proving any of these. So I'll stop now for questions, and thank you very much.
Thank you very much, Alexey, for a nice talk. And now if there are questions, please go ahead.
I have a question.
Yeah.
Where does the barrier come from, the n over square root log n?
The n over root log n. This, where does this come from? That's a great question. Do I have an answer for that? I'm not sure I have a good answer for that off the top of my head. Sorry. I think the log comes from the fact that you have this 3 to the t everywhere. I'm not sure where the root log comes from though. But yeah, good question. Again, feel free to follow that up with me later on this one.
I've got a related question, which is, if you were prepared to make one of the errors a bit worse, could you make the other one better?
That's a great question. Yeah, it's interesting. I haven't thought about that. Probably, let's think. So you mean in this version of the theorem, right? Rather than the one I took.
Yes, so yes, exactly. Sort of, I wonder whether you just optimized two parameters to make them the same, or whether it wasn't like that.
Yeah, the truth is I just didn't think that much about optimizing the bounds. I would guess if you make one of the bounds worse, it should be possible to make the other ones better. But how much better? So certainly we can't get rid of this term at all, right? Because then you'd get disjoint bases. So no matter how good we make this bound, you can't really get independent sets of size n. This I did think about, and I didn't see a way of doing that. But could you get something significantly better? It's a great question. Yeah, I think that's worth thinking about.
If you use your theorem as a black box, can you derive partial results for the two problems on that slide?
For these ones, not that I'm aware of, but I wouldn't exclude the possibility. So in my paper, I also had a third problem, which was, I think it was problem 1 in the paper. And for that one, you can use it as a black box. So Matic 1 pointed out to me that you can just solve it using this theorem as a black box. But for the problem 1 in the paper, which was, I think the statement was that you find n, you want to find n disjoint rainbow independent sets of this size. I think that you can black box it from the theorem. So that's actually a bit related to what Tim was asking. So I think maybe this error you can improve. But for these ones, I think they're genuinely harder. But yeah, so particularly this one, I think it needs new ideas. This might be a good starting point for doing these, but it will need new ideas, I think.
Your result does look a lot stronger to me.
Then what? Then
your result looks a lot stronger than the n/2 result.
Yeah, but also actually getting full basis it's not. That's also difficult. Like
right.
So I think there are like non-trivial difficulties to getting them into full basis. I've tried kind of combining the arguments from the two, and I couldn't see how to do it. Again, I think that's like with these problems, I haven't tried that hard, so I think they're worth working on to try and see what you can do. I think there's definitely potential to black box things.
Thank you.
I was also going to ask if you think these two problems are independent, the two problems you put there. So it looks to me like the first one's probably harder, but
Yeah, I think they are independent, right? Like, yeah, even with this covering thing, is it so easy to prove things there? Yeah, I've spent more time thinking about the first one, so this when you want actual basis, than or the second one. But yeah, I've no idea about. I would encourage people to think about them. I think once we have like one asymptotic version, it should be easier to prove better ones because you can kind of start rearranging things, starting with an asymptotic. Plus, there's also potential for doing various absorption type techniques, like in some other rainbow decomposition problems. So there's all sorts of things you can do starting with this.
Okay. If there are no further questions for Alexey, let's thank him again for a very nice talk.
Thank you.
Thank you.